Welcome friends for the second day of circuit simulation and PCB designing workshop. So in this webinar, before starting the second day, I will revise what we have learned on the last day. So we started with the basics of simulation software. So what are the different simulation softwares we have? Then we have covered around 2022 different simulation softwares and the features of those particular softwares we have covered yesterday's session. After that, we started with Proteus 8.9 features and the overview of Proteus 8.9. So what are the features of Proteus 8.9? What the things we can do with the Proteus 8.9? Then we studied developing step, like downloading steps of the Proteus 8.9, how we can download the software and how we can install the software installation steps of that as well. Then we started with some discrete electronic simulations, like yesterday we have did voltage divider simulation again, just by using registers, how you can simulate it, how you can animate it, that we have explained yesterday. Again we have seen regarding alternator simulator, then some transformer related simulations and all. Okay, so I will start the next day session. Before starting the session, I will introduce myself. My name is Niraj B Kapase. I have done my master's from University of Surrey in the field of mobile and satellite communication. Currently, I am working as assistant professor in DKT's Textile Engineering Institute, Rajwada, Isarkaranji. Okay, we'll start with the with the first circuit. We start with the basic switch operation, how our switch works. So I have opened the proteus. Now I will go to a schematic capture. From this particular window, we need to select the component. So I need the switch as a component. So I will click on a component, click on a parts, type switch. Once you type a switch, there are different switches available. So we require a single pole, single throw switch. So SPDT. So either you can choose this switch active, that is SPST, that is single pole single throw switch latched action. So we'll have a symbol of the switch, no PCB preview possible available. So we'll see that how to assign that as well. Now we require one battery, so type again a battery. So select battery active DC voltage source, click OK after this. Now we require a lamp, so type lamp, then selected the lamp active, this is the symbol of lamp. Okay, now put the battery in the circuit. So we'll zoom it, battery in the circuit, then we require a lamp at the other side and then the switch. Okay, now for connection, go to selection mode and then just turn over mouse over here. Your pointer will turn into the pin, connect it. Okay, done with the connections. Now I can save this particular design. Just hit a save button. We'll create a folder. Create on the desktop, new folder. We'll rename it circuits. CR03. Save it. Now if you want to run this particular thing, we can run it directly by here. Now it's running, the current is not flowing, circuit is incomplete. Once you press the switch, circuit is complete and the bulb is on. You can review off. Again, once you press, bulb is on. Again, if you release it, bulb is off. Now we can do animation as well. Go for the animation, just stop the simulation here, go to system, click on set animation option, tick these two options like show wire voltage by color and show wire current with arrows. Tick these two options, click OK and again run. Now you can observe that circuit is not completed, the button is not pressed. Once you press it, the circuit gets completed and then the light is on. Okay, so this is very simple circuit, but for understanding this very useful. Okay, thank you. Now we'll see the next circuit. As potentiometer operation, so we'll connect a potentiometer and then we'll test the potentiometer operation. For that I will close this particular thing, and then we'll start with a new design. Okay, for the potentiometer operation we require a battery. We'll see how the current is flowing from the circuit and use of a potentiometer. So I will type a battery, select again battery active. Okay, then again we require a lamp, LAMP, type lamp, so select this lamp, animated light bulb. Okay, again we require a potentiometer, so pot dash linear, we require linear change. So either linear you take, or just you take this pot HG, that is high granular interactive potentiometer, linear, logarithmic, or anti-log law. So, okay, so the circuit looks like this. So I'll put a battery first, I will zoom it. Okay, then we require a potentiometer, so we'll turn it to tilt this particular thing, either use numpad plus symbol. So I have tilted it. Okay, so then we require a lamp, so I'm going to connect the lamp at the outer side, output set. Okay, I'm going to connect this with a wire. Okay, this and this, done. Now you can have a potentiometer is having 3 terminals, so either you can short it on this side or on this side. So if you short this on this side, so earlier the potential, when your pointer is at this particular point, you will apply a full resistance in the circuit. When your pointer is at this particular point and your connection is at this side, you are applying less resistance in the circuit. I will show you what will happen. So I will change the resistance. So I will change the resistance to 10K. Okay. Now I will go to a system, set animation option, then wire voltage by color and wire voltage by arrows. Click OK after this. Click on run. It's running now. Bulb is not on because it's having a resistance. So if I increase the resistance, you can observe the resistance is increases. So you'll have 100% resistance appear because your connection is like this. So 100% resistance is there. So 10K. There is no action on the bulb. So once you decrease the resistance by clicking it here, so like you are turning the potentiometer, you can observe the light is on. Okay, this is on, light is on, and this is full bright when there is a zero resistance, and whenever there is a little resistance, the light is having less intensity. So it's very simple circuit. Also you can test instead of light, you can test a fuse as well. So how the fuse blow off due to heavy current pass from that particular line. So for that what I will do, I will remove this. How to remove it? For that, double right click on the device, that device will be removed. So I will go to a parts and type fuse, FUSE. So once you type a fuse, so we'll have an animated live fuse model. So this is animated model. So select this fuse active animated fuse model. So click OK after this and put the fuse here. Okay. So I will keep a fuse. I will connect this in the circuit. Okay, circuit is completed now. I will increase the resistance first. So currently I have resistance of 87. So I will run it again. For running, I will click here to run this. Once it's run, the fuse is okay. Okay, you observe this particular fuse. Okay, I will run it again. So I will decrease the resistance in the circuit. At some level, the current start flowing from the circuit, and then it's like a short circuit. When there is a very low resistance, the current is heavy whenever there is a short circuit. Observe it. Still not. Okay, have you observed it? Once it is zero, the fuse is blown off because of it is a short circuit. Like positive terminal of a battery is connected to a negative terminal because you are making this resistance zero. Because of this fuse go off, and then this circuit gets disconnected. Okay, so this is about the fuse. Okay, now I will save this particular circuit. This, save it, go to desktop. There is a circuits CIR04, will make save. Okay, all right. Okay, in the next circuit we'll see switch operation, SPDT switch operation, which is generally in case of stairs we have one switch can be operated as a turn on, also that same switch can be operated as turn off. So how the circuit is, so we'll see that. So click on a component mode, click on a parts, so type SPDT. So once you type SPDT, so there is a switch, interactive switch available, switch active, interactive. Okay, so we'll click OK after this. Now we require battery again, so we'll type battery active DC voltage source, click OK. We require lamp, we'll see that lamp again, we'll take a lamp. Okay, click OK. Alright, so the circuit schematic is like this, so I will zoom this. Okay, battery is kept, SPDT switch. So I have two switches, so one I will connect like this, another I will connect like this. Okay, and then the lamp I'm connecting at the output side. Okay, so one terminal I'm going to connect it here, this is going to connect it here, this will be connected to here, this is connected to here. Okay, this is the circuit for SPDT switch operation. Okay, we'll go to a system, set animation option, show wire voltage by color, wire voltage by arrows, click OK, click on run. Now we can observe there is no current flow from the circuit because this switch is not on. Now you can make of this particular switch to turn on. So for that we need to connect like this. So this is on, so I can on the circuit. Now the circuit is on. Okay, if I want to make it off, just this is the ground floor, look at this is at the top floor, I will make it off. Okay, alright, then while coming I can again press it, this makes on, while going I can press it, this makes off. Okay, so you can operate this SPDT switch in both the ways, to turn on as well as off. Okay, now I'm going to save this circuit. Okay, now in the next circuit we'll see how the relay operates. For that the components required, we require one battery, so we'll select battery active DC voltage source, click OK. Then we require relay, type relay, so select this relay active, so we'll have many relays available, so select active. We require one single pole only, so there are two options, double pole, so double turn on, so we require single pole, so select single pole relay. Then we require a lamp, so lamp is there. Okay, then we require one switch to turn on this, so we'll type switch or a button, you can put anything. So switch is available, click OK after this. Alright, so the circuit connections are like this. So we'll have a battery at the primary side, so I will zoom it and draw the circuit. Sorry, it is a battery. Then we'll have a switch connected to like this. So relay is having 5 terminal device, so I'll explain this about relay. A relay is having 5 terminals, so these 2 terminals are for coil, so these are the for primary side or a low voltage side, and this is are the higher voltage side. So here it is a common terminal, and these 2 terminals are, one is normally closed and one is normally open, so you can connect your circuitry towards this. So I will show you how to connect it. So like this, I need to connect here. Okay, so this primary side is completed. Whenever I presses this particular switch, the current flows from this coil. Because of this, this relay energized, and this switches from normally closed to normally open, or normally open to normally closed. Okay, so that depends on again user how he's going to operate that particular thing. So I will put a lamp on the output side, so I'll connect this to particular this. Okay, alright, so this is the circuit completed. So now I need to simulate it. So before simulating, I will go to a system, set animation option, click this particular two options, click OK. I will save the design first. So go to this, go to desktop, circuits, circuit 06 will have this. Okay, so I have already said that, so I will turn on the simulation. Now the relay is off because no current flowing from this particular coil. So once I hit this particular switch, the current gets flowing from this coil and then the relay will turn on and the bulb will be automatically on. You can observe this. Once I remove this, the relay is off. Once I take it, it is on. Relay is used for isolating your low voltage circuitry with a high voltage applications, like by using a microcontroller. If you want to turn on 230 volt AC supply on 50 hertz supply, or you need to control a motor or induction motor, you can use a relay over there. So this is very basic circuit and the circuit schematics are like this. Okay, so here it is. I have used 12 volt relay. There are different relay modules available which works on either 12 volt, 5 volt, 6 volts, like this. So depending on your voltage ratings, you have to choose your relay. All right, so I will stop simulating this and then I will save this particular circuit. Okay, next circuit we'll see a transistor as a switch. So we require transistors. So either you can use BC547 or directly there is a standard transistor available, NPN. Just type NPN over there. So we'll get a standard simulating model transistor. So here it is, a simulated model transistor, NPN transistor. So you can use any of the transistor from here. So I'll use generic device transistor, bipolar transistor. Click OK after this. Then we require some battery. So select a battery active DC voltage source. We require some resistors. So type RES. So once you type resistors, so we'll have different resistors available. So we don't care about the PCB design now. So we'll keep as it is, the schematic and all. So I will keep OK for the resistor, and then we require some lamps. So I'll put a lamp and select this LED lamp and click OK. Okay, so the circuit schematic is like this. Again, we require one SPDT switch to show the operation. What is the effect of the transistor acting as a relay? Okay, so first we'll put a battery, maximize this. Okay, then we'll keep an NPN transistor here. Then we require a resistor, base resistor. I will keep this little bit bigger circuit, so like this. Alright, so I'll take this at their side. Then we require SPDT switch, so I'll connect the switch like this. Okay, so lamp is required, so I'll put a lamp, I'll rotate it, put a lamp. I'll use another transistor to show how, if I connect the base directly to the VCC, what will happen. So I will rotate the resistor. Okay, so of 10K, that doesn't matter. So rotate it again. The second lamp is there. Okay, so I will connect all the circuit. So first lamp, then second lamp, then first lamp goes to collector of first transistor, second lamp goes to collector of second transistor. The base is driven by directly a VCC. Then all the emitters are connected to the negative terminal of the battery. This is connected to here, the base of second transistor. Now what I can do is, this is connected to this. So I have two terminals to be connected. So one terminal I am going to connect it to this, and another terminal I am going to connect it to a ground. Okay, so here you can observe that. So this is transistor Q1 and transistor Q2. So once I run this particular circuit, the transistor Q2 gets on because it gets a base current. So we'll see the current through the directions. So for that, go to a system, go to set animation option, click show wire voltage by color, show wire voltage by arrows, click OK, and then directly run. You can observe this. The current flows from this particular transistor because it's having base current flows. Because of the base current, light is on. Now if I switch this particular thing, once the current flowing from this second transistor, now automatically the bulbs get on because transistor gets on. Okay, the circuit flows completed like this. Alright, are you clear with this? Use of a transistor as a switch. So like this you can operate transistor acts as a switch. Okay, so I will stop simulation, go to save option. I will save the circuit in the folder circuit with the name CIR07. Alright. Okay, now we can simulate some of the gates. For that we require a gate, so we'll take gate. So basic gates we'll see first, AND. So we'll see AND gate simulation model. So here it is. Sorry. So just type AND, enter. AND gate simulation model, or just type OR. Okay, so OR active, two simple input OR gate symbol is available, and the NOT required. Just type NOT single digital inverter. So IC numbers are also available, so you can use any of that. So for giving the input, there is option here is a logic gates, logic state. Logic state will give input, so here it is an input option, and logic toggle is also there, momentarily action. So we'll have a logic state, and to observe the output we have logic probe. So again type logic probe. So select that logic probe big. So I've selected this. Okay, click OK after this. Now go to AND gate. So I will put a like this AND gate. Here it is OR gate and the NOT gate. Okay, so three gates I have kept, and OR and NOT. So I'll give output side, I'll connect a probe to check the output. So I'm going to connect like this, I'm going to connect like this, I'm going to connect like this. Now for the input side, input states, logic states, so I'll give the states like this. So these are the two states for me. These are the two states for OR gate, and this is one state for NOT gate. Okay, so I'll connect like this, give the input for this, and for this as well. Okay, done with this now. Now we can simulate it, you can run it directly. Look at the AND truth table. When both inputs are 0, the AND gate will give a 0 output. When any one input is 0, then also the AND gate will give you 0 output. So you can check when both inputs are 1. So I will change the input here by pressing it here. When both the inputs are 1, the AND gate will give you 1 output. Okay, we verified the truth table of AND gate. Similarly, we verify the truth table of OR gate. If any one input is 1, the OR gate will give you 1 output. So if I click it here, the OR gate will give you 1 output. Click it here, OR gate will give you. Again, it is inverted. So when my input is 0, my output will be 1. When my input is 1, my output will be a 0. So all the truth table is verified. You can do like this simulations of basic gates as well. Okay, so we'll stop simulation and we'll save this particular thing. Alright. Similarly, there are two universal gates. One is NAND gate and second is NOR gate. So we'll see we can prepare basic gates using universal gates. So before that we'll simulate NAND gate. So I will type NAND. Okay, so this is a symbol of a NAND gate and we'll get a NAND gate. I will click OK. Okay, so this is NAND gate. Alright. So if I want to make this NAND as an NOT, so what I can do is I can short these two particular inputs and then I can operate logic probe. Type logic probe big, I will use big. So there is no difference between smaller and big, only the size difference is there. So larger version is better to see, so we'll take that. And logic state, so is the input, so we'll select this logic state. So this will give you NAND as an NOT gate. So now you can look the verification. So if the input is low, my output is high. Okay, similarly. Alright, it's done with NAND as an NOT. Now we'll see second part, that is NAND as an AND. Okay, for that again I will check NAND as an AND. I will take one input. It requires two NAND gates, so I will make this input as a short, give here. So I will use this inverter circuit here, and then logic state will connect it here like this. Now states I am going to connect it like this. There are two inputs, input A I am giving here, input B I am giving here. Alright, so A and B are the inputs for the first AND gate. Then secondly I am using inverter. Okay, two AND gates, I can do NAND as an AND. So I will run it again, will test. Now both the inputs are 0, my gate AND gate will show you 0 output. When both the inputs are 1, then only the AND gate will show you 1 output. When any one of the input is 1, AND gate output is 0. When both the inputs are 1, the AND gate output is 1. So let's test it now. Okay, now we can do AND as an OR. Okay, we can do AND as an OR. So how to do that? For that, the circuitry, here it is, one AND gate, another AND gate. Okay, so I will give the output of this AND gate to this, of this AND gate to this. Okay, then I will short this particular two inputs. I will short this particular two inputs. Okay, I will connect logic states here, one state, another state, and I will connect logic probe advance and output. This connection is done. Now this connection is done. This connection has been done. Okay, now I'm going to run this. Now my both inputs are 0, my output is 0. When any one input is 1, the OR gate output is 1. So look at this, is 1. When another input is 1, then also the output is 1. So this verifies your NAND as an OR gate. Okay, so this done with the basic gates simulation. So we'll save this particular thing. Click on a save, click on desktop, go to circuits, then this is circuit 9, so CIR 09, so save it. Alright, now we'll see a sequential circuit, like using a D flip-flop we'll create a traffic light simulation. So for that we require a component as D flip-flop. So I will type DTFF, D flip-flop, that is D flip-flop active model. So here it is a D flip-flop, we have Q and Q bar. Okay, then we require a traffic light, so I will type traffic light. So we'll have a traffic light simulation here. Then one more thing we require is logic gate, AND gate. To do the logic we require AND gate, and we require a clock. So we'll type clock. To run this particular thing we require a clock, so we'll select this particular clock. Okay, alright, so AND gate, clock, D flip-flop and traffic light is required. So now the circuit schematic I will draw. So I will zoom it. It is a D flip-flop, the second D flip-flop I need to keep it here. Okay, and then the traffic light at the output side. Okay, one more AND gate is required. So this AND gate I need to keep here. The AND gate give input to the green light, so Q bar is my input to the one AND gate and Q is the another input for my AND gate. Okay, then this Q will go to orange light. Okay, then this Q bar will go to the red light. Okay, then this Q bar is shorted with the D, connected from here. Okay, again this Q bar is shorted with this D. Okay, then the clock is given towards this AND input. So this second clock is available from this particular Q bar. Okay, so I'll connect it like this. Now I will connect the clock here. Okay, now I can change the clock frequency, keep it 1 Hz, so it will take 1 second to turn on and off. Now you can simulate. The circuit gets completed. Now you can simulate. Click here, run it. Now you can observe red, orange, and then green. Okay. Alright, so this D flip-flop toggles every time. So based on the clock, it toggles, and then we have done this AND gate logic such a way that it will, when it is a green, it's off, and then again switching like this when red, orange, and the green. Okay. Alright, so done with the circuit. Save the circuit. Okay, close this. Now we'll see some motor examples. So some interactive motors we'll have, like DC motors. So we'll type motor. So we'll have a DC motors available. So once I type a motor, we have different types of motor, like BLDCs are there, BLDC triangle is there, Adafruit motor hat is also available. We have motor like DC motor, stepper motor controller. Then we have stepper motor is available, simple DC motor active with fan, 3-phase motor is also available. So like this, many motors are available. So we'll select DC motor, simple DC motor model. We'll select this model. Okay. So I will select active model so that it will run accordingly. So I require one particular battery. So many of you have already worked with some robotic kind of application. So we'll see that application now. So for that we require forward and reverse movement of the robotic car. So we require SPDT switch. So select SPDT. So type SPDT, interactive SPDT switch. Click OK after this. Alright. So I will show you the circuit connection schematic. Okay. So first of all, take a battery. I will maximize this. And motor is at the output side. So I'll keep the motor here at the output side. SPDT switch, so I'll rotate it like this. So second switch I will connect it here. There are two switches. One switch is connected to this particular point. The another switch is going to connect to this particular point. Then this I'm going to connect to positive terminal. This I'm going to connect it to negative terminal. So this is shorted towards the positive terminal. This is shorted towards the negative terminal. Okay. Once I run it, you can turn on the animation option. So I'll click OK this animation option. If you run it, now its motor is off. The direction is forward. Look at this. Okay. Alright. So direction is reverse. Okay. So like this we can do. I can stop it from here as well. Okay, forward direction, this is reverse direction. So you can observe the direction of the motor like this. You can zoom it. Alright. So this is motor simulation. So you can do a simulation of a motor as well in the proteus. So there are different applications. So I will show you some microcontroller based applications as well afterwards. So how you can simulate microcontroller based application, microcontroller based traffic light as well after coming circuits. So stop this particular simulation, save this particular thing. So go to this. Circuits. Okay, done with this now. Well, now we'll see some oscilloscope based applications. Like very first application is half wave rectifier application. So for that we require a diode. So commonly we use 1N4007 diode. So select this 1N4007. So I'll select the silicon rectifier diode with maximum peak reverse voltage is 1000 volt, and this. So I'll select this. This is the footprint of the diode. So I'll select this. Then we require some AC input source. So I'll type alternator. So I'll type alternator. So select this alternator. So alternator is available. Or you can type V sign as well. So I'll show you that as well. V sign is there. So this is again a sinusoidal waveform source. So both you can use. So we require one load resistor. So I'll type register RES. I'll use this. Okay, the circuit schematic is very simple. For half wave rectifier, we have one alternator, one diode only, and then the output side one resistor. So I will rotate the resistor by pressing a plus symbol. I have rotated it and I will connect it here at the output side. Okay, I'm going to connect it now, this to this, this to this, and this to this. Alright, so connection has been done. Now in this particular mode, so we have virtual instruments. So go to virtual instrument mode. Here it is available. So go to oscilloscope and choose the oscilloscope. It is a 4-channel oscilloscope. One channel we are going to connect it to the input, and another channel we are going to connect it to the output. So this is yellow line is an input and blue line is an output. So we can configure this particular thing as well. So it is here, it is 6 volt with 1 hertz. Okay, so we'll keep as it is and then just click on run. Once you run it, you will observe the oscilloscope window. So I can turn on time per base knob here, so you can observe the different waveforms. So it is a half wave rectifier, but you are observing this as an double waveform. So why? Because the ground is not there for the circuit, so we need to keep the ground. Suppose if I close this particular oscilloscope here, okay, I have closed it intentionally, I have closed it. I will show you what will happen. So I'll put a ground. Okay, again I will run. The oscilloscope will not observe. So for that, the oscilloscope is available in debug. In a debug, last one is oscilloscope. Now you can observe, here it is. Okay, here it is, and you can move the waveforms on and up and down as well. Okay, like this. You can observe the voltage drop. So you can make it DC. Okay, you can switch the channel to a DC. Then this is AC signal. You can make it ground first. Okay, this is ground. Now you can make this channel as a ground as well. Okay, both the lines you should match. Here it is, matched lines. Now I'll switch this to a DC. Now I'll switch this to a AC. Okay, you can observe, right, the cycles will come. You can observe the voltage change or voltage, less voltage. This voltage is this difference of voltage due to the diode consumption. So 0.7 voltage drop is there across the diode. So you can observe this. So you can maximize this as well. So you can maximize this. So I have kept voltage as 6 volt only. That's why it's a problem. And also there are different options with the oscilloscope. You can have print this particular waveform. So click on a print. So it will ask you which printer you are going to use. So directly I have connected to HP2050 or any other printer. Epson I have. So you can connect it to any printer, or you can just print it to a PDF as well. So we'll see by printing a PDF. So select Microsoft Print PDF, then print it. Once I hit on a print button, so it will print information. So we save in the same circuits, half wave rectifier, SWR. So I have saved it. It is done. Okay, also if you want to change the color of this, you can go to a setup and then change the colors, the printer color and all. So if we can change printer color, we can change channel color, we can have different markers. So there are different markers available. So like this we have a cursors, so we can put a cursors, like it will display voltage and all the things. Like here you can observe 6 volt, and if I put another cursor on this particular line, so you can observe on the top it's having 5.3 volt, something like this. Okay, so these things you can do with this particular oscilloscope, and it's very powerful tool as well for simulation. Okay, now we'll see the PDF as well. So we'll go to a desktop, the circuit, the PDF is created already. Okay, so here it is, SWR PDF. Once I open it, you will get very nice waveform there. Look at this. Okay, this and all the detailed information about this as well. So like output and all, what are the things where you set your channels and all. So here it is a DSO output. So standard DSO output you will get directly. Okay. Okay. Similarly, you can simulate full wave rectifier as well. So same components are there. We can take oscilloscope and then we can simulate it as well. Now we'll see some interactive simulations, like some IC based simulations. So we'll see a counter, very important application in many of the industries, many of the schools, colleges, and everywhere. So the counter. So for that, we'll see using a discrete components. So for that, we require 4511. So 4511 is a CMOS BCD to 7 segment decoder. So we'll select this BCD to 7 segment decoder, which we are going to connect one 7 segmented to it. Then we require 4024 as a decade counter. So here it is 407 stage binary ripple counter, or a decade counter we call it as. Okay, so we require one 7 segment display. So we'll type 7 seg. So once we type 7 seg, we have common anode, also common cathode type of display. So we'll select common cathode type of displays. Click OK. Okay, then I'll show you the circuit schematic. One more thing we require is a clock. So go to a parts and type clock. So select this particular clock. Okay, 4024. All right, then we require 4511. Keep some distance, and then we require 7 segments. So I'm going to connect the 7 segment at this particular line. Okay, so like this. So another facility of a proteus is, once the lines connections are same, so you can directly double click. So this will be fine. Okay, are you getting this now? Okay, all right, so I'll make it a little bit closer. Okay, now I'm going to connect 4 signals, A, B, C, and D. Okay, done with this now. Okay, so I'm going to give a clock to the input. So this is not connected. It shows connected, but it's not connected. It's connected now. Okay, all right, the LT and BI I need to short and connect it to plus 5 volt. So I can give voltage from here as a DC voltage source. So I'll connect it like this. Double click on this. I'll give 5 volt. Okay, then this LE will be grounded. So I'll choose a ground from here and connect a ground. Now I can run this. There is no output. Why? Because I have not connected ground for the common cathode type of a display to connect it to the ground. Okay, so it start counting. You can look. So it's 1 hertz clock signal. So for each second it's going to change. Now it's 3, 4, 5, 6, 7, 8, 9, 0. Again it's a blank. Why? Because it's giving a clock, but it's a blank. Why? Because we have not reset it. So it will count till 15. So we need to reset at 9, this particular thing. So how to reset that? For that, the logic is, again, go to component, select one AND gate. Okay, so my 10th count is 1010. So I'm going to select 1010 from this 4 states. So 1010. So this is a MSB bit. So I'm going to connect it this and 1010. So I have connected these 2 inputs. Okay, I can change the frequency. So if I make it fast, if I want faster, I'll make it 2 hertz. You can observe now it's a faster than previous one. Now after 9 it's going to reset. Look at this. Okay, it's reset it. If I want to do a multi-digit counter, okay, this is a single digit counter. If I want to do a multi-digit counter, what I can do is I can select this particular thing. I will just drag and drop a little bit down. All right. So again, I require a second digit. So for that, I require again 4024. So I'll use 4024 here. Then again, I require 4511. I'll use 4511 here. I require 7 segment. Use a 7 segment here. Okay. Then clock is not required because this is 9. Then it has to generate a clock from this particular reset. So I will use this reset particular button to give a clock to this. This 4 inputs are connected. Okay, this is connected to this. Sorry. sorry, okay, it's connected, it's connected, connected. Okay, now the ground is, I'm going to connect it to ground. I will use same ground, so don't worry. Then VCC, I'm going to connect it to VCC again, so I'll use same VCC, and I will use same ground. Okay, it's a little bit complex, but you can do. We require again to reset this particular thing as well, so I'll use again AND gate and then master reset the thing. Okay, then again this is this thing. Okay, now I can run. Now you can observe I have made clock as 2, so it's 0, 9. It's a multiplex display, 1 1 1 2 1 3 1 4. You can observe once it is 9, it will trigger from this. When it is high, this will trigger towards this. Okay, so you can observe this by increasing this. Instead of that, I will make it 5 Hertz. Okay, and I will increase one more display. Okay, I will save this particular thing first before increasing. Go to desktop, go to circuits, CR13, save it. For 511, then gate. I'm connected to a ground. This is this. Okay, now the clock is input from this particular reset. Now one more AND gate is required to reset this particular upper display. New. Okay, whenever it's not fitting in the schematic, so it will ask you whether you want to replace the component. No, I will to keep that component as well. You can now run. You can observe now the frequency is 5 Hertz, so the counting is very fast as compared to previous one. You can observe the things. This digit is 0, rest of the digits are changing. Now what you can do is you can arrange this particular digits in one particular line like this. You can drag and drop, so wiring will be as it is. Sorry. Okay, now it's moving. Okay, now 3 digits displays are here. Okay, I have completed the 3-digit display. Now I can change the count towards 10 Hertz so that you can observe third digit as well. I will maximize this. I will run this particular thing. Now you can observe the counting is very fast, and you will have a very accurate results for this as well, like 60, now 70, 80, now we'll have 90, and again 103 and 4. This counter is still 999, so we can design any stopwatch using this. So I will give you 1 Hertz generation as well. So here simply I have used 1 Hertz. So either you can use quartz crystal, or you can use just RC oscillator to generate 1 Hertz, or you can use 555 circuitry to generate 1 Hertz as well. Okay, so there is very easy circuit. So I'll show you one schematic which I have already prepared using this particular IC as a clock. So I'll show you that. Here it is. I have designed the same circuit with the 5 digit counter. So circuit is too big, so I'll show you the maximizing display like this. If I run it, you can observe the counting. It will display the 5 digit counter. You can have like digital clock as well by using this. Okay, it's very simple circuit. Now we'll see a BCD counter. So with the BCD components we can do BCD counting digits as well. So for that we require 74LS390. So select 74LS390. It is a dual ripple counter. Okay, so we'll select that dual ripple counter. So select it. Okay, all right. So we require a BCD 7 segment display. So I will type again 7 seg. So we require a BCD display. So we'll select this BCD display, BCD 7-segment binary coded display. We'll select that. Okay. Now the circuit schematic. Again, we require a clock as well. So we'll click on a part and type clock. Select this particular clock. Now we'll do a circuit schematic. So I will show you only a single digit. So here it is. We'll have BCD. We'll put a BCD. Q0 connected to Q0. This is Q1. This is Q2. Sorry. This is Q3. Okay. Then clock P is connected to Q0, and I'm going to give a clock towards this. Okay, and I can run it. 0. It's not counting forward. Why? We'll see. We need to give logic state. For the master reset, so we'll use one more BCD 7 decoder, one more BCD display. I'm going to connect this to wires, this Q3, Q2, Q1, and Q0. Okay. Now I can operate master reset by using this logic state. So I can connect that master reset with the logic state. Okay. Now clock A I will give from this particular Q3 output, and I will give clock B from here. Okay. It's connected now. Now I can run it. Now we can observe the things. Now I have misplaced the displays, that's why it's counting like this, but you can do first display on this side and second display on that side, so that will be fine for counting. Okay, so I will correct it first. I will extract it here and put it here. So this display should be on this side and this display should be on this side. Okay, it's done now. We will click it here, sorry, and run it now. Now you can observe it start counting 0, 1, 2, 3, 4, 5, 6, 7 like this. So it's very easy circuitry. Only one IC is required, that is 74LS390, and then the clock. So it's a BCD counter, so we require BCD displays. Okay, so like this. All right, so easy circuitry. I will save this circuit. Circuit 14. Okay, now we'll see a flasher circuit. Again, I will click on a schematic capture. It will open. All right, for the flasher applications are many. So we have bikes, cars, so indicators uses a flasher IC. So it's very basic IC they use, that 555. So 555 is a timer or oscillator IC. So select this. So it's a 8-pin IC DIL socket available. So we can have different packages as well for this as well. So we'll select this DIL package. Okay, so here it is. 5. Okay, we require another components as LED. So we'll type LED. Then there are different animated LEDs available. So we'll select red LED. So select red, click OK. If you require another color, you can choose. Again, type red. And suppose if LED, type LED. If you require, like suppose green LED, so you can select green LED. If you require blue LED, select blue LED as well. So we can have different colors LEDs as well. So select this. Yellow is there. So yellow is there, so I will type LED again. So I'll select low as well. Okay. Another thing we require is register. So type RES and select register. Okay, register generic device. Click OK. Then we require capacitor. So type CAP as a capacitor. So select capacitor as generic device again. Okay. So these are the components we require. Okay. So the circuit connections are like this. So 8 and 4 is shorted. 8 and 4 is shorted. 3 is output. So we are going to connect output to all the LEDs. So I will put the LEDs here. Okay, 1, 2, 3 and 4. Sorry. We'll choose multi-color LEDs. So blue is there. So I'll click green here, red here, and yellow here. Okay, so all the cathodes I am going to connect it to the pin number 3, that is output. Anodes I am going to connect it to VCC. Select VCC. So VCC is available in terminal mode. Go to power. Power is again a VCC, so select this power. Again, for 8 and 4 we require to give a power, so I have connected that. Again, 7 we require one resistor, and then connect 7. So I'll rotate the resistance, so I'll keep resistance like this. So this is need to be connected to a 7. Then second terminal I need to connect it to VCC. The resistance value is 1K, so I will double click on it. We will change the value 1K. Click OK. Then one more resistance is required in between 6 and 7. Sorry, move this here. Okay, so I will connect this, and 6 and 7. One more resistance is required. I have connected it. The value of this is 470. Okay, so I will put 470K for this value. Okay, one capacitor is required, and that capacitor is at this particular point, and the second terminal of 1 nanofarad, and the second terminal is connected to a ground. So I'll select the ground, connect the ground here. Pin number 1 is again connected to a ground, so I'll use one more ground here. Both ground are same, you can connect it like this. So pin number 2 and 6 are shorted, so I'm going to short pin number 2 and 6 through this. Okay, so pin number 5 is open, pin number 4 and 8 is shorted, rest of the things are connected like this. So I can run it. Okay, you can observe the LEDs are flashing. So this is a flasher. So it's very basic circuitry we can observe using a flasher. Just 3-4 components are required for constructing a flashing circuitry. You can try this at your home as well by creating a small PCB, and the PCB size of flasher is very small, so we'll generate a PCB of this circuit as well. Okay, so have you understood this circuit? Okay, then we'll save this particular thing. Go to this circuit, then circuit 15. Okay. So this particular thing. All right. Okay, now we'll simulate some op-amp based circuitry. So we'll start with a new design. Okay, so we require op-amp. So either you can use 741, LM324, OP07 like that. So but standard op-amp is OP-AMP. I'm going to use for standard simulation. So I will use those op-amp at animated model. Ideal op-amp I'm going to use ideal op-amp. Then we require a battery, so we'll select battery and type battery. So battery active DC voltage source, click OK after this. Then we require lamps, so we'll see plus VSAT and minus VSAT of op-amp, that is positive V saturation and negative V saturation. Then we require pot linear, so we'll put a pot dash HG, so this is interactive pot we'll have. We'll connect a battery like this. So we'll zoom this. Sorry. Okay. Two batteries are connected. This I'm going to connect like this. Then the ports are connected to op-amp to both the terminals. So it's having two terminals. One is inverting, non-inverting. So I'll connect like this. So port HG, one port at this terminal, another port at this terminal. Okay, one port I'm going to connect it to non-inverting terminal. One port I'm going to connect it to inverting terminal. Okay, then lamps I'm going to connect it to towards output side. This is lamps. I'm going to connect it like this. Complete the circuit. Very basic and interactive circuit, so that you can understand much more things in this circuit. Okay, so now what we can do is we can put two voltage measures here. So I'll little bit move, I will move this particular thing little bit this side. Okay, so that I can attach, I'll move this particular thing as this side as well, this towards this. Remove the wire. For removing the wire, just double right click, connect, so that the circuit looks nice. We have a DC voltmeters available, so go to this virtual instrument mode. Here it is. Go to DC voltmeters. So both the voltages we are going to measure. So here it is. One voltage is for non-inverting terminal. Another voltage I'm going to connect it to the inverting terminal. Okay, and one voltage is at output side. Now we'll observe the voltages as well and the effect of inputs. This center is grounded, so I will connect a ground here. Alright, so I will run this now. Once I run it, both the inputs are 11, 11, so everything is 11. I can move. Okay, whenever the inverting terminal input is more, sorry, non-inverting terminal input is little bit more, you can observe it is 12, 11.9, 11.9, both are same, no issue. When it is 12, immediately the output goes to plus VSAT. Because of that plus VSAT, this LED is on. Alright, whenever this is less, the output goes to minus VSAT. Look at this, minus 3.01, this LED is on. Alright, so little change will make the sense. Okay, also these things, are you observing the thing? Okay, so this is op-amp simulation. Op-amp has a plus VSAT and a minus VSAT. So I will save this particular circuit. I will stop the simulation and save this particular circuit. CIR 16. Okay. Okay, that's all for today. So feedback link is given in the description bar. Also, I have shared the feedback link in the chat window. Now you can give feedback for the today's session as well. And one request is, those who have not subscribed my channel, just press subscribe button and press the notification bell icon for next upcoming updates for you. So in the next session, what we are going to see, we'll see a graph based simulation, we'll see a microcontroller based simulations, how we can embed a hex file in the code and all. We'll see sub-circuit mode simulation, so how we can do a sub-circuit mode simulation as well. Then some projects like water level controller, USB connection projects, how we can read some memory cards and all. So those kind of things we can see. Some interactive simulations like how we can interact hardware with the proteus as well. So like connecting Arduino to the proteus directly, and the proteus is given data to the Arduino as well. So I'm going to demonstrate that tomorrow. Then PCB designing steps. So how we can design a PCB of all the circuits. layout drawing in the PCB, auto routing, manual routing, design rule check, and 3D simulations. Okay, so these are the contents of next day. So stay connected. Again, those who are not subscribed my channel, please press a subscribe button to subscribe and get next upcoming updates of next webinars. Okay, thank you for listening. So these are my contact details. So you can write me a mail on nirajbkapase@dkts.com as well. Okay, so I will keep this feedback link open, so you can give a feedback for today's session as well. Okay, the feedback link is available in the description bar. Also, the feedback link is available in chat box. Thank you for listening patiently.